In this video we are going to see an example of second order circuit. In this particular problem we have asked to find out the voltage across the capacitor. Now let's look at the given problem. Here this question is asking, for the following circuit the switch has been at position A for a long time and moves to position B at t is equal to 0. Find the output voltage Vc of t for t is greater than or equal to 0. Okay, so first we have to write our initial conditions. So in the initial state we have the switch at position A for a long time. It means the capacitor will be fully charged and it will act as an open circuit. Okay, so there's no current through this one, and if we draw the new circuit, let's go ahead and draw the new circuit. So this is going to be our new circuit, and here we are going to have our voltage source. This is our resistor, and here also we have a resistor, and then here also we have a voltage source, and this inductor is going to be short circuited because it has been sitting here for a long time. It's going to be short circuited. Now let's go ahead and draw the diagram. So this is our voltage source, this is 28 voltage, and here we have 4k ohm resistor, and this is our 12k ohm resistor, and this inductor will be short circuited, and this is our voltage source 20 voltage, and this capacitor will be act as open circuit. Okay, so we are interested in the voltage across this capacitor, V of t. Now the first thing is we have to find out what is going to be the current through the inductor and also the voltage across the capacitor in the initial state. So to find the current through the inductor, what we can do is we can use the Kirchhoffs Voltage Law, because in the initial state it's series, so current everywhere is going to be same. So Kirchhoffs voltage law says that voltage in should be equal to voltage out. In our case 28 plus 20 is the voltage in, 28 plus 20 is the voltage in, and voltage out is going to be addition of these two resistors. That's going to be 4 plus 12, that's going to be 16k times I0 minus. Now if we solve for I0 minus, we are going to have I0 minus is going to be equal to 48 divided by 16k, and that's going to give us 3 milliampere. So this is the current we have before we switch, like before we flip the switch. Okay, so this is our initial current through the inductor, and also we have to know what is the voltage across the capacitor in the initial state. So if we calculate the voltage in this area, that's going to be the voltage across the capacitor. Now let's go ahead and do that. Here we have 28 voltage, so 28, okay, let's put V0 minus, that's going to be this 4k times 3 milliampere. Let's assume current is in this direction, so 4k times 3 milliampere minus 28 voltage. So 4 times 3, that's going to be 12. Milli and kilo cancels each other. 12 minus 28, that's going to give us negative 16 voltage. So this is our initial voltage. And after we flip the switch, these values don't change immediately. So we can say I0 plus also the same value. And also we can say V0 plus is also the same value. Okay, so this is our initial condition. Now after that we are going to create the differential equation. Here we have to have second order differential equation because we have second order circuit. We know this is a second order circuit by looking at the energy storage devices. When we have two energy storage devices, for example here we have capacitor and inductor, so this is a second order circuit, so we will have a second order differential equation. Okay, so in order to create the second order differential equation, we have to know two equations. These are the two main equations in order to derive second order differential equation. Okay, so first of all, VL, voltage across the inductor, is going to be equal to L di IL over dt. So when you have voltage across the inductor, you can replace this one with this one, and also I of t, we can replace that one with C d V of t over dt. Okay, so these are the two important equations we have to know in order to bring our second order differential equation. Now let's go ahead and create the second order differential equation. So when we create second order differential equation, we consider the switch is flipped because we are trying to find the voltage across the capacitor after the time is equal or greater to 0, because when the time is equal to 0, the switch has flipped, so the circuit is going to be different right now. So let's go ahead and draw the new circuit. So this is going to be our new circuit right here, and in this one you can see after we flip this one, we have here we have two resistors. Like you can see these two are in parallel. We can combine them directly, but just to show you, I'm gonna draw for right now. So this is two are in parallel, and here we have this capacitance, and also we have this inductor, and also we have the voltage source. That's it, right? So let's go ahead and draw this one. So this is our capacitance, that is 8 nanofarad, 8 nanofarad, and this resistance is 12 kilo ohm, and here we have 24 kilo ohm, and here we have 200 millihenries, and this is our 20 voltage source, 20 voltage. Okay, so here you can see these two resistance are in parallel. So when we have resistance in parallel, we can do the product over sum. So 12k times 24k divided by 12 plus 24, that's going to be 36k, right? 36k. So this one is going to be 3 times of this, then this one is going to be 6 times of this. So we can replace, actually 8 times 8 times 3 is equal to 24. So 8k is going to be the equivalent resistance for these two. So we can replace this one with 8k. Okay, so this is our 8k resistance right here. Now we can create the equation using Kirchhoffs voltage law. Kirchhoffs voltage law says that voltage in is equal to voltage out, or addition of all the voltage in a loop should be equal to 0. These are two valuable statements for Kirchhoffs voltage law. Now here we can say this 20 voltage is the voltage in, right? This is our voltage source. So we can say this is equal to x of t. So we can create x of t is equal to addition of all the other voltages. Voltage across the inductor plus voltage across the resistor plus voltage across the capacitor. Voltage across the inductor, we are going to use this equation. The first equation, L dIL over dt. So L dIL over dt, and voltage across the resistor, we can use the Ohm's law to write this one as I of t times R, because V is equal to IR. So voltage across the resistor is I of t times R, and voltage across the capacitor, that's what we are interested in. That is, we are given in terms of V of t, so let's keep it as V of t. Okay, so the next thing is we have to bring everything in terms of V of t. Okay, because since we are interested in finding the voltage across the capacitor, that is in terms of V of t, we try to bring everything in terms of V of t. Now let's see how to do that. And here the equation I of t can be written as C dV of t over dt. So that's the one I'm going to use right here. So this IL, if you look at this one, this inductor in series, right? So if we say I of t is the current flowing through this one, so the current through the inductor should be also I of t. So instead of writing IL, we can write I of t, because all the current in this series is going to be same thing. So instead of writing two different terms, we can say I of t. And if I replace that I of t with C dV of t over dt, this is going to become L C d square V of t over dt square. Okay, and here we are going to have x of t, and this I of t, I'm going to do the same thing. I'm going to replace this one with C dV of t over dt. So here already you have R C dV of t over dt, and here we have plus V of t. Now we have brought our second order differential equation. Now the next thing is we have to bring the standard form, because this is not in standard form. If you look at this one, here we have a coefficient in front of this highest order. We shouldn't have that one. So in order to get rid of this one, what we do is we divide everything by LC. In that way we will have a standard second order differential equation. Okay, so let's go ahead and do that one right here. If we divide everything by LC, this is going to be x of t divided by LC, and then here we are going to have d square V of t and divided by dt square. Then if we divide this RC by LC, that's going to become R over L, right? Plus R over L dV of t over dt plus V of t divided by LC. So this is our standard second order differential equation. Now let's go ahead and plug the values. Okay, here we have LC. LC is the inductance times the capacitance. Inductance in our case is given by 200 millihenries, and the capacitance is 8 nanofarad. So 200 millihenries, milli is 10 to the power of minus 3, 8 nanofarad. So times 8 times 10 to the power of 9 farad. So this one is going to give us 2 times 1.6. So 1600 times 10 to the power of minus 12. So that's going to be 1.6 nanofarad. Okay. So we are going to divide this 1 over 1.6 nanofarad, and if you divide 1 by 1.6 nanofarad, that's going to give you 625 megafarad, right? So mega. So this is the one we are going to have. Now let's avoid the unit for now, because this is in, so this is, the whole thing is going to give us different value, because 200 times 10 to the power of minus 3 is henries, right? Henries times farad. So let's keep the mega for now, and for this one we just keep the value as it is, and also we have to multiply this one with x of t, because we only took L and C, right? So we have to multiply this one with x of t, and that's equal to d square v of t over dt square. And here we have the resistance. Okay, let's look at the resistance. 8k divided by L. In our case, L is 200 millihenries. So if you divide 8k by 200 millihenries, that's gonna give you 40k. So this one is going to become 40k dv of t over dt, and then here we are going to have v of t, and that one also divided by 1.6 nano, so that's also going to become 625 mega v of t. Okay, so this is the equation we derived. Now let's try to simplify this one. Our next purpose is find the general solution for this non-homogeneous differential equation, because this is non-homogeneous, because after the equal sign we don't have 0. So this is a non-homogeneous, right? So when we have non-homogeneous differential equation, what we do is, to find the general solution, we find the homogeneous solution, and also we find the particular solution, and we add them together, right? So in that way we will get the general solution for the non-homogeneous differential equation. To finding the particular solution is easy, because if you treat this v of t as a constant, and if you take the derivative, this one will become 0. Okay, this one will become 0, this one will become 0, and if you solve for this one, 620 mega v of t is equal to 620 mega x of t. This 625 mega cancels each other, so we will get v of t is equal to x of t, and we know that x of t is equal to 20 voltage, so 20 voltage is going to be the particular solution. So Vp is equal to 20 voltage, and now we have to find out the homogeneous solution. To find out the homogeneous solution, what we do is, we take the characteristic equation, okay, and we find the real roots. Now let's go ahead and do that, but before we do that, we have to know what kind of system this is, because there are 3 kind of system. You can have overdamped system, underdamped system, critically damped system. It depends on what kind of zeta value you have. So we have to check the zeta value for now to find out what kind of system is this. Now to find that one, you can compare this. This is our standard equation, differential equation. So whatever the value you have in front of this v of t, that's going to be the omega n square. In our case, that is 40 v of t. In front of v of t, we have 625 mega v of t. So that's equal to, like, this is omega n square. So omega n is going to be 25k, right? Because if you square 25k, you will get 625 mega. So omega n is equal to 25k. So if omega n square is equal to 625, and k, this, if you compare this one, the value in front of x of t, that is k omega n square. So if omega n square is equal to 625 megavolt, and if the k also 625 mega, k omega n square, you can see the k value must be 1, because in that way only we can have omega n square and k omega n square same value. So K is also equal to 1. Now we can find out our zeta value. Here 2 zeta omega n is the value in front of dv of t over dt. And in our case that's 40k. So let's go ahead and figure it out what's the value it is. So let's get rid of these parts. Okay, let's get rid of these parts and continue right here. So here we are going to have 2 zeta omega n, that should be equal to 40k, and we know that omega n is equal to 25k. So 2 zeta 25k is equal to 40k. Therefore zeta value is going to be 40k divided by 50k, and 40 divided by 50, that's going to give us 0.8. So 0.8 is less than 1, right? So when we have less than 1 zeta value, that's going to be underdamped system. So this is an underdamped system. Okay, so when we have underdamped system, our general solution for the differential equation is going to be this pattern. It's going to be like c e power negative sigma t, right? Negative sigma t sine omega dt plus theta. So this is going to be the general solution for the differential equation pattern. Okay, so since we are trying to find homogeneous, now first we have to find out the real roots. Now to find the real roots, we have to use the characteristic equation. Now let's go ahead and do that one. Okay, so here we have r square. Okay, let's do that. So r square plus, I have to get rid of some part because we have so many things going on right here. Let's get rid of some part right here in order to solve this one. Okay, I erased my initial condition. We have to remember initial condition. I of 0 minus is equal to 3 milliampere, and also V of 0 minus was negative 16 voltage. We need these two later. Okay, now we have to find our characteristic equation. Now let's go ahead and do that. So this is going to be r square. We replace the second order with r square and first order with r, and whatever the coefficient in front of it, we keep it. So this is going to be 40k, and then 625 mega, that's one is going to be equal to 0. Okay, and if you solve for this r, you have to use the quadratic formula. If you do that, you are going to get negative 20k and plus or minus 15k. Okay, 15k. So these are, when we have this complex number, the complex number comes like that: negative sigma plus or minus omega d, right? So omega d, so in our case omega d is going to be 15k and sigma value is going to be 20k. So we are going to plug that value in this equation. So we can say our homogeneous solution for the differential equation is going to be c e power negative sigma t. In our case sigma is negative 20k t, and then sine omega dt. Sine omega d is 15k, so 15k and t. After that theta. Here we have to find out our c and theta value. Now this is a homogeneous solution for the differential equation. Now we can write our general solution for the differential equation, because we have the particular solution, that is 20 voltage, and also we have the general solution, I mean homogeneous solution. We can write our general solution for the non-homogeneous differential equation. Okay, now let's go ahead and write that one. That one is going to be 20. Okay, let's write this p of t, that's going to be equivalent to 20 plus c e power negative 20 kt, then sine 15, so this one should be in bracket, so 15k plus theta. Okay, so this is going to be our general solution for the non-homogeneous differential equation. Now we have to find out the particular solution for the non-homogeneous differential equation. To find that one, we have to find what is our c value, and also we have to find what is our theta value. So to find this one, we are going to use our initial condition. That's why we found out the initial condition. This is I of 0 is equal to 3 milliampere, and also we have V of 0 is equal to negative 16 voltage. So we are going to use this two information to figure out what is our theta value and also what is our C value. Now let's plug the first condition. First we are going to plug V of 0. Okay, let's plug V of 0 and see what we get. So when we plug V of 0, this is going to become just 20, and this is going to become just C, because e power 0, because the time is 0 at the time. And also we can say V of 0 is equal to negative 16. Negative 16 is equal to 20, and the time is 0 at that time, so this is going to be e power 0. E power 0 is just 1, so this is going to be just C. And then sine 15k, I forgot to put t right here t. So this t is going to be 0, therefore this is going to be 0, then we are going to end up with sine theta. Okay, so this is our equation 1. Now what we are going to do is we are going to apply the second condition, initial condition. And also you have to remember that when we have I of t, we can rewrite this as C dv of t over dt, right? So we can say I of 0 minus is equal to, or 0 plus, is equal to C dv of 0 plus over dt. Okay, so here what we have to do is first we have to find the derivative, and let's write this one. So I of t is equal to C dv of t over dt. In our case, C is what? C is the capacitance. Let's look at the capacitance. Capacitance is 8 nanofarad, so we multiply this one with 8 nano. Then we take the derivative of this function, and if you take the derivative with respect to t, this 20 is going to be 0, because derivative of a constant is going to be 0. And if you take the derivative of C e power negative 20 kt, that's going to be just negative 20k multiplied by C e power negative 20 kt. Then we keep the other one as it is, because this is going to be a product rule, because we have two functions related to t. So the first one, we take the derivative of first one first, then we keep the other one as it is, then we take the derivative of other one, then we keep the first one as it is, right? So we have to do that. So first we took the derivative of first one, we keep the other one as it is, so this is going to be just sine 15 kt plus theta, and then we are going to take the other derivative. So other derivative, when we take the other derivative, we keep the first one as it is, so this is going to be C e power negative 20 kt, and when you take the derivative of other one, that's going to turn into cos. So this is going to be cos 15 kt, and here we are going to have chain rule, because we have to take the outside derivative and also we have to take the inside derivative. Outside derivative is going to be just cos 15 kt plus theta, and if you take the inside derivative, that's going to be just 15k, right? So we have to multiply everything by 15k, and that's it. So this is going to be our derivative. Now what we have to do is we have to plug 0 for t and see what we get. So here we have 8 nano, and also C dv of t over dt, that's our current, right? We wrote this one in terms of current, and we can replace this with 3 milliampere. So let's put 3 milli, and that's equal to 8 nano. And if we plug 0 for these t values, this negative 20k remains, and this C remains, and this e power negative 20 kt is going to become e power 0, because the time is equal to 0. So if this is e power 0, e power 0 is just 1, so we don't have to write this one, right? And also sine 15 kt, kt is going to become 0 because of the t0, this is going to be 0, so we will end up with sine theta. And here we are going to have C e power negative 20 kt. So here C remains, and e power negative 20 kt is going to become e power 0. E power 0 is equal to 1, so we don't have to write that one. And here we have cos 15 kt, t is going to be 0, so this 15 kt will be eliminated. Then we will end up with cos theta. Okay, cos theta multiplied by 15k. So this is what we derived. Now let's try to simplify this one in order to find the angle. If we divide 3 milli by 8 nano, 3 milli by 8 nano, let's see. Let's get rid of these parts because we need some space. Okay, so let's continue this one right here. Okay, so first we are going to bring the 3 milli divided by 8 nano, and then after the equal sign we have negative 20k c sine theta, and also we have plus c cos theta 15k. Okay, so when you divide 3 milli by 8k, you're gonna get, okay, when we simplify, we get this one. We get 15kc cos theta. 15kc cos theta is equal to 3 milli over 8 nano plus 20 kc sin theta, and therefore c cos theta is going to be equal to negative 23. Okay, actually I am going to turn into tan theta. Let's get rid of this one. So if you solve for, if you rearrange this and make this one tan theta, because we have cos theta and sin theta, if you bring it into tan theta, that's going to become 36 divided by 23. Okay, 36 divided by 23, therefore theta is going to be 57 degree. So we have theta, and from this theta we can find out the c value, because initially we created the equation that's negative 16 plus equal to 20 c sin theta. Therefore c sin theta is going to be equal to negative 36. So we can say c is equal to negative 36 divided by sine 57 degree. Okay, sine 57 degree, and that's going to give us negative 42.72. Now we have the c value and theta value, so we can express our particular solution for this non-homogeneous differential equation, and that's going to be our final answer. So therefore the voltage across the capacitor is going to be V of t. That's going to be equal to, the particular solution was 20 minus 42 point, I'm bringing this equation. Okay, this was our general solution. Now in the particular solution we are going to include the c value and this theta value. So this is going to be 42.72 e power negative 20 kt sine 15k plus 57 degree. Since the time is greater than or equal to 0, we have to multiply this one with u of t, and that's going to be our final answer. I hope this helps. Thanks for watching.